Welcome everyone to today's webinar from HoliSoils on the monitoring of organic soils. Before we start, one or two organizational notes. If you have any questions during the talk, please write them down in the Q&A box you find in the bar below. We will answer all of them at the end of the session. Please do not raise the virtual hand because for the recording it's better if we have everything put together in writing. And with this we can start. Today I'm really glad to welcome Aleksi Lehtonen from Luke, the Finnish Natural Research Institute, here for our webinar on the monitoring of organic forest soils. A few words to introduce Aleksi. He's a research professor at Luke and he acts as a principal investigator for various projects, including HoliSoils, but also other projects on forest soils and carbon dynamics. And we are really glad to have Aleksi because he's not only working here in HoliSoils as an expert, but for years before he already worked in the field on greenhouse gas reporting in forests and forest soils. And this also includes reviewing methods for the IPCC and leading the team at Luke that is responsible for greenhouse gas inventory work in the LULUCF field. In HoliSoils, he's a deputy coordinator and leads the work package 4. And work package 4 is responsible for all of our research sites and the data acquisition from those sites. They all monitor closely the data according to different research questions depending on the sites. And in the next minutes, he's going to tell us more about the importance of monitoring of organic forest soils from his experience over the last years, including HoliSoils. And with that, welcome Aleksi, and thank you for being here.
Okay, thank you, Vera. I'm happy to be here, and yeah, let's get started. So, project is HoliSoils, and about my title is monitoring of peatland forest soils, and here I'm mentioning few colleagues, but there's a long list of people that have been contributed into the slides that I'm showing today. HoliSoils stands for Holistic Management Practices, Modeling and Monitoring for European Forest Soils. And peatlands have been studied here in Finland, but also in Germany within the HoliSoils. And then about the content of my talk, first I will touch a little bit on the EU policies that relate to the forest soils and greenhouse gas exchange. Then some slides where we are now with peatland mapping in Europe. And then I would like to say something about the peatland greenhouse gas monitoring, especially based on the Ranskelankorpi, which is our experimental site here in Finland. After that, I will conclude my presentation. About the EU policies, science is able to provide solutions to enhance soil health and develop sustainable forest soil management practices. And here you can see the list of the policies that address soil challenges. So we do have the EU soil strategy for 2030 that sets the target that all soils in the EU are healthy by 2050. And provide steps for protecting and restoring soils and ensuring their sustainable use. Then we do have also this soil monitoring law with the aim to create coherent monitoring framework for all soils. Then we do have nature restoration law, LULUCF regulation, common agricultural policy, and proposed forest monitoring law. All support soil monitoring, mitigation, degradation, and fostering restoration. And we think that the science provides enhanced understanding for soil processes and their drivers and ecosystem restoration practices and soil monitoring frameworks, which all are needed for the effective implementation of these policies. In addition to these policies that I just mentioned, I would like to raise one more, and this is the permanent carbon removals, carbon farming, and carbon storage in products, often named as a CRCF regulation. And the aim of this regulation is to develop voluntary union certification framework for permanent carbon removals, carbon farming, and storage in the products. And here in the middle, this is just copied from the regulation text. So the carbon removals and soil emission reductions should be quantified in relevant, conservative, accurate, complete, and consistent, and transparent and comparable manner. So there's a lot of conditions here and requirements, meaning that we need to have really state-of-art tools to monitor greenhouse gases and their changes that are resulting, for example, from the management interventions. And now we have the first set of methodologies under commenting. It's a delegated act. There is not much about the forests there, but there is something. Planting trees, and also on peatlands if that's done for restoration and re-wedding case. And then there is also peatland re-wedding and restoration on agricultural soils. But this means that there will be in future new methodologies coming, maybe not next year, maybe year after, which may include actions like improved management of forests. While now current set of methodologies is more focused on the agricultural lands. Then why all these policies and why do we have it? This is a work by EFI and Hans Werkkerk et al. From 22. It's a report by the European Forest Institute showing that we have different land-based mitigation strategies, noting though that all those have high uncertainties, but there is also, I can praise a few of those, like forest restoration on peatlands, and also other active management practices. So there are tools in a toolbox that can contribute to the climate change mitigation, and the potential is quite significant at the European Union level. Then monitoring. I think first condition for the monitoring is that we need to know where do we have those peatlands. And here, coming from Finland, we do have a lot of those. And here you can see aerial photos from our study site Ranskälänkorpi, from the left corners, up corner, starting 1960, only a few ditches. 1980, already more ditches. And 2008, you can see that trees have been growing maybe better. And 2025, you can see the clear cut on the right. And actually on that clear cut, we have our ecovariance tower for peatland monitoring. If you look at the European level, Baltic Sea Basin is the area where we find a lot of peatlands and peatland forests. And we do find those also British Isles, Scotland and Ireland. And on the right-hand side, you can see the map where we do have most of the peatlands and even also the permafrost areas within Europe. This is the UNEP 2022 Global Peatland Assessment. And then about the emissions and sinks, this is now showing this figure here, mineral soils and peat soils emissions and sinks in forest lands. So if you are above the zero line, it means that it is a sink, carbon stock is increasing. So most of the red bubbles are sinks. Most of the member states have a sink in their upland soils, mineral soils, but then these kind of blue bubbles are mostly below the zero line. So most of the member states are losing soil carbon from their forest peatland soils. And the size of the bubble is illustrating the area of forests, either on mineral soils or peat soils. Mineral soils being the red bubbles and the peat soils being the blue bubbles. The x-axis is the area which is in logarithmic transformation. And maybe kind of takeaway from this figure is that few countries have quite significant areas and significant emissions and sinks. And when the methodologies are improving, these values can change and they can have a high impact also to the EU level budget. As you can see on the right hand side, we do have like approximately 25 million tons of CO2 emissions from peatland soils in the European Union, while the sink of upland soils is about 100 million tons. So when these numbers are getting more precise, methods are changing, so those will very likely change. And maybe from the figure you can see that we do have countries that have a smaller role with the soil emissions and less land area, while we do have lands or countries where these are really significant. So this is a work that my colleague Aura Salmivaara has been doing. So this is a Baltic Sea region trained peatland mapping. We do have a global peatland map products. What is novelty here is that we want to have information if those lands are drained or not. And Aura is working with that. She's been working that with HoliSoils project, and she's continuing that with the OGCR project, which is a Horizon funding. You can see the footnote for the whole title. It relates to carbon farming. And the idea here has been to combine the remote sensing products, national forest inventory data, and airborne laser scanning data to produce maps with a high resolution for trained and untrained forested peatlands. And this is something that is very valuable when we want to find where do we have these locations and where could we change the management, where could we do things differently. We need to know where do we have those land areas. So this is a long list of Earth observations and other data, but the idea has been to put things together, like forest classification, map products for the soil types, canopy height models, multi-source national forest inventory data for tree height and also for pine volume or the volumes by tree species. And then in all countries we don't have these data, but we can substitute some of the data with some other data sources. And the idea is to segment these satellite images to have uniform management units and to be able to know if that's on a peatland or not. And then the airborne laser scanning data is to be used to detect ditch network. And this is based on the William Liedberg's code from the SLU. And the idea is to automatically detect ditches and overlay that with peatlands, forested peatlands. And here you can see some testing with Sweden, Finland, Latvia, and Poland. So this is a work ongoing, and Aura Salmivaara knows much more about it. But for Finland, how that does it look? So we have been segmenting, or Aura has been segmenting with colleagues this forest land area based on the canopy height model and dominant height of trees and the volume estimates that we have from our multi-source national forest inventory. And the segmentation looks like this. And then we do have the volumes per segments. We can estimate also the change in volume between two different time points. And then on the right-hand side, you can see the end result when it's linked with this ditch detection. We can see areas where we have dense ditch spacing, average sparse, and areas that have not been drained. And this kind of information with high spatial resolution allows us to target different measures precisely. Then about when we know where do we have those peatlands, then what we can do, we can monitor the greenhouse gas exchange of those lands. And this is actually a photo from Ranskalankorpi where we have some automatic chambers also in order to measure the soil fluxes. And why we need to monitor these carbon stock changes and other greenhouse gases from these lands. For example, the Finnish case, peatlands are so-called key categories. They are significant source of emissions, significant land area, and they are managed lands. They are drained, and therefore we need to monitor those, and we should have a higher tier method for that monitoring because it's a significant land area here. So monitoring peat's carbon change with stock measurements nearly impossible. Therefore, flux measurements are more often used. This means that we may have a peat layer that its depth is several meters or even more, and then taking cores out of that and comparing the development over time with the material that fluctuates according to the water quantity and other factors. It's very difficult to really make comparisons based on stock measurements. And for the flux measurements, we do have other challenges that I come shortly. But then if we look the greenhouse gas inventories and the IPCC guidelines, these guidelines have methods that allow countries with different level of detail to do their reporting. So to start with, we have tier 1 method, which is default emission factors by so-called ecoregions. For example, we can have one factor for the boreal drained peatlands, maybe for nutrient poor and nutrient rich lands, one or two emission factors for those areas. Then if a country is moving for a tier 2 methods, then they have a country specific factors. And in a tier 3, you have either repeated measurements or state-of-art modeling. And about these methods, measuring here on the left is a figure where we have been taking a sample from the peat layers down to 1 meter, which is in some cases that's all of the peat layer. In some cases that's just a fraction of that. And with the high spatial variability in peat properties, the repeated sampling is really challenging. And here in the middle below, you can see the automatic chambers that we are using to have a high temporal coverage. On top, you can see aerial photo of our clear cut. And on the right-hand side, you can see the Finnish Meteorological Institute EDI covariance tower in a forested area of the peatland that we are monitoring. On top of these 3 methods, we do monitor greenhouse gas exchange on these peatlands also with the so-called manual chambers that allow us to be very mobile, and we can visit different corners of the peatland area for the soil fluxes. I was trying to put some pros and cons for different methods. These manual chambers are very good for the spatial coverage, but for the temporal coverage, we often need to upscale the results. We need to measure proxies like soil temperature and soil moisture in order to be able to upscale these momentary measurements, for example, for the growing season sums or annual sums. I wrote there that not for N2O. Our understanding is that the N2O estimates based on these manual chambers and EDI covariance are very different, and for many reasons. These N2O emissions are so episodic from these lands that they are difficult to capture with these manual chambers. And with the chambers, you get part of the ecosystem fluxes. You don't get the whole picture, but you get some part, either total soil fluxes or so a proxy for the soil heterotrophic respiration if you use so-called trenching approach. While the automatic chambers, you don't get much of the spatial coverage. You need to have electricity and you need to have gas analyzers close by. But what you get the temporal coverage, so you get really nice time series out of that. And again, this is part of the ecosystem fluxes, especially if you have a fully stocked tree stand. The trees are totally excluded out of that, those fluxes. Then the EDI covariance for greenhouse gases, you have a spatial coverage, but it varies. So the footprint area depends on the wind direction and wind speed. So, and that's a kind of its own field of science to estimate the footprint areas for these EDI covariance towers. You get good temporal coverage, and it's nice for N2O. It's including all kind of surfaces, not only undisturbed surfaces. That typically this manual chamber data, they have mostly undisturbed surfaces, and therefore might provide kind of a underestimation for the ecosystems that have also disturbed surfaces. And you get the full ecosystem fluxes, the downside being that it's quite expensive to set up and maintain that kind of instrumentation. Then I jump into the case Ranskalankorpi, which is a drained peatland. Here you see Scots pines. Actually, Ranskalankorpi is dominated with the Norway spruce trees. And for the background about this drained, why we have been studying for this Ranskalankorpi, we do have a lot of these lands, these drained peatlands, about 4.7 million hectares. About half of the peatlands were drained, and a lot of them are approaching the time of final felling. And they were drained to increase wood production, mainly from 50s to 70s. But at the side product, there has been and there is these negative environmental effects like nutrient loading, greenhouse gas emissions, and loss of biodiversity. So here you can see the figures. You have a pristine drained peatlands, and then on the right-hand side, we do a monitoring on these lands. So this is Ranskalankorpi. This is a clear-cut area where we have a lot of monitoring. Now we want to understand what are the emissions of the clear-cut and compare those against a control, which is kind of a no fellings. And then we have a treatment where we have a selection harvest, kind of continuous cover forestry. We want to compare these different management units against each other. I will showcase some of the results that are mainly done by Olli-Pekka Tikkasalo and Olli Peltola. So here you can see the clear-cut measurements for greenhouse gases for 2022. On the top, you can see, on the top panel, you can see the CO2 flux, the variability with the yellow with the ecosystem respiration, and the green one being the cross-primary productivity, while the green line being the kind of net ecosystem exchange, and the black line being the cumulative fluxes. And you can see that we are losing a lot of carbon to the atmosphere from these systems as a CO2, while the methane in the middle, it's smaller if you look the units on the y-axis, while again N2O is actually quite significant if we look the amount of N2O, and especially when you convert that to the CO2 equivalents by using global warming potential. So CO2 emissions are more than 20 tons of CO2 per hectare, while N2O makes like approximately 5 tons as a CO2 equivalents per year during 2022. And that's all reported in that Tikkasalo et al. Paper. And our N2O emissions, they are clearly higher than in prior studies. If you look at paper by Minkkinen et al., which was this kind of undisturbed forest stands, those do have much smaller N2O emissions than these that have been recently harvested. While our CO2 results, they are in line with prior studies like Korkeakoski et al. From 23, which was done in another location, but with a similar site type. Then if you look, clear cutting was done in 2021, and the CO2, the cumulative net ecosystem exchange, here grams of CO2, you can see that it's approaching zero. So we are 22, we had the highest, then 23 is less than that, and 24 even less. And then if you look kind of a time series of the CO2, we can see 22 on the left. Again, most of the dots are above the line, so we are losing carbon, while we have some sinks, small sinks there as well. Already 23, the contribution of sinks has been increased. This site was planted with Norway spruce seedlings, so those are starting to grow, and also understory vegetation has an important role. Its site is recovering and it's getting green and greener and greener. And then 25 this summer, we had even much higher sinks. We did have some emissions, but also significant sinks. And the 25 budget is still unknown because the year is not done yet. For the methane, you can see a development like that. So we do have some emissions, but also some uptake. And then there's some noise, of course, with the instrumentation. These are to be analyzed still. The Tikkasalo paper is analyzing these for 22, but the other years are still not thoroughly analyzed, and these are preliminary results from Olli Peltola. This is N2O, and quite interestingly, after forest operation, we have quite significant emissions that are reduced 23 and reduced quite a bit for 24, and now 25 were much smaller. So it seems that N2O in Ranskalankorpi is phasing out in few years. Then for the end, I would like to take an example that we did earlier, kind of taking these kind of measurements and using them with the forest simulators and look what happens if you transition from rotation forestry and clear cutting to selection harvesting on these fertile drained peatlands, and what it would mean for Finland if you would keep the harvesting levels as they have been. So you would provide the timber for forest industry, but you would change the management in small fraction of the land, and the fraction being here fertile drained peatlands. So you would go for this kind of even age management to continuous cover management. And here on the top line, you have this kind of traditional management, clear cutting of even age stands, while in below you have this continuous cover management, and you avoid maintenance ditching. And we studied the impact of this conversion, and we could see that for Finland we could reduce the emissions by 1 or 1.2 teragram of CO2 annually when we would avoid clear cuts on these fertile drained peatlands. And yeah, and that we could see that the regions are very different depending on what kind of forests they have and where do we have kind of a mature, fertile, trained peatlands. Those areas differ. And what was also interesting here was that the quite high contribution out of that 1 and 1.2 teragrams was that trees were growing better according to our Mela simulator, because we are avoiding this young seedling stand phase. And in that continuous cover scenario, our harvesting area was larger, and because we were doing this kind of selection harvesting in various locations. And some of the clear cuts from peatlands were translated to the upland soils. But still, we got higher or less emissions or higher sinks by doing this. So this isn't just an application that is building on these measurements and the monitoring. And I think I'm close to end, so I would like to conclude. So we have several EU policies that relate to the peatland forests. So the importance would be that we ensure the coherence between these policies, that they are not contradicting or creating incentives that would be taking our peatland forest to different directions. And what we have learned is that the forest management makes a difference for soils, especially with trained peatlands. One can reduce greenhouse gas emissions by managing water levels. Maybe one lesson from Ranskalankorpi that was learned, that the site that had very deep water table to start with, continuous cover forestry was able to increase that water table a bit, but not enough. So maybe in future, more efficient management for water tables are needed. Mapping of peatland is improved with the modern tools, like this airborne laser scanning is really interesting tool for ditch detection. And then happy to see the results from the edicovariance-based peatland monitoring, because that allows us to compare different management practices, and it's also very nice when we are able to measure the N2O from the edicovariance, which is kind of giving the full picture from very different kind of surfaces that we do have on these clear-cut areas that are typically not measured by these manual chambers. Maybe with this one, I would like to close my presentation. Thank you for your attention.
Thank you, Aleksi, for this very nice talk. And I'm not sure if the audience or some people from the audience were here yesterday, but I think this showed quite well how different the monitoring from mineral soils is from organic soils. And yeah, we have some questions in the chat for you. At first, there is a question, I think I'm just going to read it. I wonder about the feasibility of peat carbon stock measurements. You mentioned that monitoring carbon stock changes using stock measurements is nearly impossible. What makes it difficult, and can the flux measurement replace the necessity for knowing stocks?
Okay. So the image on the left illustrates the stock measurements in a way. So the challenges are related to the fact that when we come back to this location, let's say after 10 or 20 years, we should find the location, but we cannot take the sample from exactly the same point because there is a hole in a peat. And then we should be able to link different layers in these peat cores against each other to be able to that we are comparing not apples and pears, but apples and apples in a way, to comparing the same layers. At 10 years, many things can happen, and the peat is kind of able to fluctuate depending on how dry and wet it is. And some of these peatlands can be very deep. So if you want to get the whole stock, you need to go down deep down. And I think these flux measurements are not able to substitute the carbon stock measurements. But if we are monitoring peatlands, depends on the purpose that we are monitoring. If we are monitoring those for the greenhouse gas fluxes, then flux-based measurements are direct measurement of these greenhouse gas fluxes, and then those are useful. While if we are measuring stocks in order to understand how much carbon do we have, then we need to probably make a stock measurement, and a lot of them, because this spatial heterogeneity is high. But for the greenhouse gas inventories and for carbon removal regulation, it's more about fluxes. How can we reduce the greenhouse? How we can still manage the land, but reduce the greenhouse gas fluxes, or how the greenhouse gas fluxes will change if we do rewetting and restoration.
Okay, thank you, Aleksi, for that. The second question is, in Ranskalankorpi, did you make ditch renovation? And then there's probably the Finnish word for it, but I cannot pronounce that.
In here, we haven't been doing this. This is owned by a forest industry company, the land, and what we have been agreed with them, we have been monitoring the clear cut control and the selection harvest, and then we have the ditch renovation probably refers to now in a clear cut area and this kind of opening the ditches, kind of uudisojitus. I don't see this chat, but something like that. Yeah. So here in Ranskalankorpi, we did so-called navero-ojitus, which is we did not so deep ditches, but that lower a little bit the water table to improve the seedlings to be established. So that kind of ditching was done in Ranskalankorpi, and I was kind of missing that. I was misunderstanding about the restoration, and the restoration has not been planned here.
Okay, thank you for that. I don't see any further questions right now. Yeah, so if there are no other questions, I think we can close the session. Aleksi, thank you again for joining us here and telling us things about the Ranskalankorpi. I visited it. It was very impressive. The size alone of this plot is very, very impressive. Thank you for talking about that, and thank everyone for joining us here. If you're interested, we will meet at the same time also online next week again, and Tiana Martinovic will tell us about soil biodiversity and why forest soil biodiversity matters. With that, I thank you again and see you next week.
Thank you. Bye-bye.
Bye.